Alright, so we finished part 6 talking about neutron stars and how incredibly dense they are, and also the fact that if a star is initially spinning, which is almost invariably true, its spin will rapidly increase as it shrinks. This is due to something called conservation of angular momentum. A neutron star should spin many, many times per second when it first forms. And the reason that's important is because in 1967, radio astronomers found objects that they eventually called pulsars. Pulsars were these objects that seemed to have radio pulses that blinked on and off with very, very rapid periods. Some were spinning more than 30 times per second. A few were spinning slowly, only only once every several seconds. But even that kind of spin reduces the possibility of the objects that these could be. Now there are variable stars. Variable stars change their brightness, but they don't change their brightness that quickly. It's impossible for something as large as a star to vary, to pulsate, for example, in as fast as 3 or 4 seconds. Certainly not in several times per second. You would need the signals to travel through the star at faster than the speed of light for that to occur. Even white dwarf stars are too large for this to occur. Perhaps you might think, well, maybe a white dwarf star that has one bright side and one dim side, if it were spinning very quickly. Well, if you calculate, because a white dwarf star is very small compared to a star, it's only about the size of the Earth, but if you calculate how fast a white dwarf would have to spin 30 times a second, the equator of the white dwarf would be traveling faster than the speed of light. And there's nothing that could hold itself together and still spin that quickly with that sort of equatorial speed. But because neutron stars are so compact, they can spin that quickly without tearing themselves apart. First of all, the gravity is much stronger, and secondly, because they're much, much smaller than a white dwarf or a regular star, they could spin that quickly without being torn apart. And so we ended up with something called the lighthouse model of a pulsar. A pulsar is basically a spinning neutron star that's going round and round very fast. Because it is spinning so fast, it could flash on and off if it had 2 bright spots on its surface, or even 1 bright spot on its surface. Well, it turns out that pulsars or neutron stars would also have extremely intense magnetic fields. And these magnetic fields, we think, actually rip electric charges off the surface of the neutron star and deposit them at the magnetic poles. When they hit the magnetic poles, they cause radiation to be beamed in 2 directions, one out the north magnetic pole and one out the south magnetic pole. Oftentimes these magnetic poles are at a large angle compared to the spin axis, just like the Earth's magnetic pole is about 11 degrees away from its actual spin axis. The pulsar would then shoot these beacons into space, radio beacons for the most part, and as they sweep by the direction of Earth, we would see them blinking on and off with a period approximately equal to the spin rate of the pulsar. So intense magnetic fields cause beams of high energy particles to stream out of magnetic poles, and then you end up when these particles crash into the surface of the neutron star, they cause radiation to be emitted, and the effect is like a giant lighthouse beacon in space. Here's a couple of pictures, more artistic pictures. The blue streams here are supposed to represent the magnetic field. The purple represent the beams of radio radiation. There is actually one pulsar that emits visible light as well as X-ray light, and that's the one in the center of the Crab Nebula. The Crab Nebula is a supernova remnant of an explosion, a supernova explosion that happened, that was observed in 1054 AD, and the central star, the remnant of the central star, is this one right here. And you can see here that the pulsar is blinking on and off. This is a very high-speed film of or video of this pulsar, frame by frame. And you can see how it goes on as one beam passes the Earth, and then it goes off as that beam does not intersect the Earth's direction. And then the other beam from the other pole is a little dimmer, and it blinks on here as it sweeps past the Earth and then goes off again. Okay, so this is like a lighthouse version of a spinning star, or an old-fashioned police beacon on top of a police car. Now, several pulsars have been found at the center of supernova remnants, which kind of nails down our suspicion that these are really remnants of supernova explosions. And also, because of the radiation going into space, there is gradual deceleration of the pulsar spin. So we think that pulsars that spin very, very fast are young, and pulsars that spin much more slowly, like the ones that spin once every 2 or 3 seconds, they are much, much older and have radiated away some of their spin rotational energy. Here, by the way, is the Crab Nebula in various regions of the spectrum. This is how it looks if you have radio eyes. This is how we see it in the visible spectrum if you have a really, really intensively good telescope. In the ultraviolet, we see the cloud of gas glowing, and this is an X-ray and gamma ray image of the pulsar. So, and the supernova remnant. So this is one of the most energetically active supernova remnants that we know of. It's also one of the younger ones that we know of. By the way, this is the pulsar that not only gives off radio light and visible light, but it also gives off X-rays. And so on the left-hand side here, this is an X-ray image, and you can see the pulsar on and the pulsar off. Well, pulsars are certainly extremely exotic objects. But we all know that there are things that make pulsars look very ordinary. Well, I don't know if anything can make pulsars seem very ordinary, and neutron stars seem very ordinary, but if you have a remaining stellar core greater than 3 solar masses, not even neutron pressure, not even degenerate neutron pressure, can counteract the intense gravity that would participate in the collapse. And so for a core mass greater than 3 solar masses, we think that the result would be a black hole. So if the remaining core has a mass greater than 3 solar masses, no known force in nature can stop the gravity. So in essence, what happens is the core, as it's reaching its final instability in milliseconds, basically, crashes through both the degenerate electron barrier, the white dwarf stage, and then it even crashes through the degenerate neutron barrier, the neutron star stage. Nothing can stop it, not the degenerate electrons, not the degenerate neutrons. We don't know of anything in nature that can stop the collapse. And so we have to conclude that this object gets smaller and smaller and smaller. And when that happens, there's a thing called escape velocity. We may remember it from the gravity chapter. Escape velocity is the speed at which you need to travel to escape the gravity, to outrun the gravity of a particular gravitational source. For example, to escape from the Earth and never return, you have to have your rocket, at least near the surface, has to be traveling at something like 11 kilometers per second to make sure that you go up and never come back down again. From the moon, it's a lot less. It would be like 2.5 kilometers per second to escape from the moon. That's why they didn't need a really big rocket to lift off from the moon when we had astronauts on the surface. And a small rocket would do. Now, light also struggles against gravity. It's not just material things that are affected by gravity. Light is affected by gravity. We don't notice this on Earth because the Earth's gravity is relatively weak. That may not seem weak when you're falling down a staircase, but basically it is very weak compared to even the surface of, say, the sun. the surface of the sun, the gravity is about 26 times as strong as the Earth. So if you could somehow stand on the surface of the sun, it would be very difficult. You couldn't stand, actually. Your joints would probably give way, and your tendons, because you would weigh 26 times your normal Earth weight. And certainly if you somehow managed to stand and you tripped and you fell, if it were a solid surface, you would probably kill yourself falling on the surface of the sun. The surface of a white dwarf star is thousands of times stronger than that, and a neutron star is millions of times stronger than that. At those kind of gravitational intensities, light struggles against gravity. Now, light is not allowed to travel any slower than the speed of light, at least not in empty space. And so what happens is, instead of going slower, it loses energy. It is redshifted to lower energy. So if you had, say, a green laser pointer that you were trying to shine from the surface of a neutron star, it would be shifted perhaps over to the yellow or the orange or the red part of the spectrum, because its photons would lose energy. And as a star collapses, the other thing that would happen is a laser beam that's parallel to the surface would start bending. And so a neutron star would bend the light. And as it got smaller and shrunk and got more and more compact, some of the light would almost start orbiting the neutron star. And once you got past a critical part, the beams of light would actually fall back onto the black hole, and they would enter the black hole and disappear. And so when the core reaches a certain size, no light can escape. And that's why we call them black holes. For all we can tell, all of the mass of the core ends up at the very, very center of the black hole, at a point called a singularity. Singularity is a mathematical term that basically means everything goes crazy there. You have infinite density and zero size, okay, which is very difficult to represent mathematically. The region around the singularity, though, is called the black hole. So a black hole isn't actually, it's hard to even call it an object, because it's really just a region of space that is cut off from the rest of the universe. A certain region of space around this singularity has an escape velocity greater than the speed of light, and so no information of any kind, as far as we can tell, can come out of it. Now, the distance from the singularity that we call sort of the surface of the black hole, or the radius of the black hole, is called the Schwarzschild radius, and that's where the escape velocity is equal to the speed of light. The Schwarzschild radius is 2 times the gravitational constant times the mass of the black hole divided by the speed of light squared. There's a very simple way of writing that equation, though. It's 3 kilometers for every solar mass of material in the black hole. So we think that the smallest black hole you could come up with the collapse of a 3 solar mass stellar core would be 3 kilometers times 3 solar masses, or about 9 kilometers in radius. So we think that the smallest black hole is about 18 kilometers in diameter. And if you add solar masses to it, for every solar mass you add to it, the black hole will grow and grow by 3 kilometers in radius. The surface of the black hole, it's hard to call it a surface because it's really just, again, a region of space that's equidistant. It's 1 Schwarzschild radius from the singularity. It's called the event horizon. Okay, so the singularity at the center is where all the mass has gone. And then 1 Schwarzschild radius from that, if you swing this radii around and make yourself a sphere, the surface of that sphere, imaginary sphere, is the event horizon. It really should be called the non-event horizon, because nothing inside that event horizon can ever get out. It is cut off from the universe. And so the black hole is anything inside this event horizon, which cannot be seen or understood from the outside. Okay, well, that's the end of part 7. We will go on to finish this up in part 8.